In this week's video, we're going to be covering Chapter 4 on joint distributions. This includes joint probability functions, marginal distributions, conditional probability functions, independence of random variables, expectations of functions of random variables, covariance and correlation coefficient, variance of a sum, convolutions, linear combinations of random variables, and its relationship with MGFs. So for those of you appearing for the CS1 exam, this video is for you. Let's start with our first topic, that is joint probability functions. A joint distribution describes the behavior of two or more random variables together. So instead of studying one variable at a time, we study the probabilities associated with combinations of values taken by both variables. Let's look at the discrete case first. For discrete random variables x and y, the joint probability marginal function is given by p of x, y is equal to the probability that the random variable x is equal to small x and the random variable y is equal to small y. Let's look at two important properties of this. The first property states that p of x, y is greater than 0 for all x, y. This means that probabilities can never be negative. The second property states that the summation over x, the summation over y, p of x, y is equal to 1. This means that the probabilities of all possible outcomes must add up to 1. Let's understand this with an example. Suppose x is the number of heads in 2 coin tosses and y is the number of tails in the same 2 tosses. Find the probability that x is equal to 1 and y is equal to 2. Also find the probability that x is equal to 0. To solve this, we start by constructing a table. The possible values for the number of heads are 0, 1 and 2, and the same applies for the number of tails. Now the probability of having 0 heads and 0 tails in 2 coin tosses is 0, since it's not possible to have both of these outcomes together. Similarly, we fill the table for all options. For the probability that x is equal to 1 and y is equal to 2, we check the table. At x is equal to 1 and y is equal to 2, the probability is given by 0. For the probability that x is equal to 0, we check under x is equal to 0. This gives us 0 when x is 0 and y is 0. 0 when x is equal to 0 and y is equal to 1, and 1 by 4 when x is equal to 0 and y is equal to 2. So we add all of these, which gives us 1 upon 4. Now we move on to the continuous case. The probability equals the integral over the range of y, the integral over the range of x, f of x, y dx dy. The probabilities can never be negative, and the probabilities of all possible outcomes must add up to 1. Now let's look at an example. The continuous random variables x and y have the joint PDF x plus y upon 100 for 0 less than x less than 4 and 0 less than y less than 2. Find the probability of 1 less than the random variable x less than 3 and the random variable y greater than 1. Let's solve this step by step using this formula. We start by integrating over the range of y and then over the range of x. The range of y here is from 1 to 2 since we are to solve for y greater than 1 and the maximum value of y goes up to 2. So that's y from 1 to 2. Similarly, for x, we are to find between 1 and 3. We then insert our joint PDF. Then, we start by solving the first integral and integrating with respect to x, treating y as a constant. Now, we integrate over the range of y. This gives us our final answer. Now, we move on to the second topic, marginal distributions. The marginal distribution of a random variable gives the probabilities of that variable alone, ignoring the other variable. Under the discrete case, the marginal PMF is given by, to find the marginal PMF for the random variable x, we take the joint PMF and perform the summation over the range of y. Similarly, to find the marginal PMF of y, we take the joint PMF and do the summation of this over the range of x. Let's understand this with an example. Consider the joint PMF of x and y below. This is the same table of heads and tails which we had covered previously. This time we are required to find the marginal PMF of x and y. So, to obtain the marginal distribution of x, we add the probabilities across each column. Then we arrange this in a tabular form. To obtain the marginal distribution for the random variable y, we add the probabilities across each row. We move on to the continuous case. For continuous random variables x and y, the marginal PDF is given by, for the marginal PDF of x, we take the joint PDF and integrate it with respect to y. For the marginal PDF of y, we take the joint PDF and integrate it over the range of x. Let's use the same example to find the marginal PDFs of x and y. We integrate over the range of y. This time we integrate over the range of x. Next, we have conditional probability functions. A conditional distribution tells us how one variable behaves when the value of the other variable is fixed. For discrete random variables, the probability of x given y is equal to the probability of x, y upon probability of y. Similarly, the probability of y given x is equal to the probability of x comma y upon the probability of x. Let's understand this with an example. Consider the joint PMF of x and y below. Find the conditional PMF of x given y is equal to 0. As we covered above, the probability of x given y is equal to 0 will be the probability of x comma 0 upon the probability of y being equal to 0. Let's look at the first case. Similarly, for x is equal to 1 and x is equal to 2, we get. After doing this, we arrange the answers we've obtained in a tabular form. Next, let's look at the continuous case. For continuous random variables x and y, the conditional PDF is given by f of x given y is equal to f of x comma y upon f of y, and f of y given x is equal to f of x comma y upon f of x. Again, let's look at the same example. This time we are to find the conditional PDFs for f of x and for f of y. The two important components of this include the joint PDF as well as the marginal PDF. We've calculated both above, so now we just insert them here. This gives us our final answer. For all the viewers, I would want you to solve the second part of this question and comment the answer below. Now that we've studied joint distributions, marginal distributions, and conditional distributions, we are ready to discuss one of the most important concepts in probability theory: independence. Two random variables are said to be independent if knowing the value of one variable gives us no information about the value of the other variable. Mathematically, random variables x and y are independent if and only if the joint PMF or PDF equals the products of the marginal PMFs or PDFs. This gives us the following formula under the discrete case and this formula under the continuous case. Here, since we're asked to check if x and y are independent, we test them at any two random points. I'm beginning with x is equal to 0 and y is equal to 0. The probability for x is equal to 0 and y is equal to 0 is given by 1 upon 9. The probability of x is equal to 0 times the probability of y is equal to 0 will be, for x is equal to 0, when we add these outcomes we get 1 upon 3. Similarly, for y is equal to 0, we get 4 upon 9. This gives us 4 upon 27, which is not equal to 1 upon 9. Since the probability of x comma y is not equal to the probability of x times the probability of y, x and y are not independent. This holds true for all points. If, for example, this equation held true for this point, it wouldn't necessarily mean that the random variables x and y are independent. If the equality is satisfied at one point, we must check at other points as well. And if it isn't satisfied at even one point, then the random variables won't be independent. Next, we move on to the continuous case. Here, the joint PDF is given by x plus y upon 100. And then we multiply the marginal PDFs which we had calculated earlier. Again, we observe that these values are not equal to each other. We now move on to the expectations of functions of random variables. The expectation of a function of a random variable gives us the average value of that function over all possible outcomes. Suppose we have a function g of x, y. We want to find its expected value. We use the following formula under the discrete case. The expectation of g of x, y equals the summation over x, summation over y, g of x, y times the probability of x, y. This formula says, take every possible value of the function, multiply it by the corresponding probability, add all products together. For example, find expectation of xy. Using this formula, we obtain Let's start with the combination where x is equal to 0 and y is equal to 0. X is 0, y is equal to 0, and the probability for them is also 0. Then, moving to x is equal to 1 and y is equal to 0, we get We do this for all 9 of the combinations. This gives us the total as 1 upon 2. Under the continuous case, the formula is the same except instead of summation we use integrals. Let's solve this example. Upon solving this integral, we get the final value as 16 upon 25. Next, we have expectation of a sum. For any constants a and b, the expectation of ax plus by is equal to a times e of x plus b times e of y. The general formula for this is as follows. Let's look at the example for this. Let's look at expectation of product. In general, expectation of xy is not equal to the expectation of x times the expectation of y, unless these random variables are independent. If they are independent, we can write that the expectation of xy is equal to the expectation of x multiplied by the expectation of y. This gives us 2 times 3, which is equal to 6. Covariance and correlation coefficient. In this section, we study two important measures that help us understand the relationship between random variables. Both measures tell us how two random variables move together. More specifically, they measure the degree of linear relationship between variables. Let's first discuss covariance. Covariance measures how two random variables change together. If both variables tend to increase together or decrease together, then the covariance is positive. If one variable tends to increase while the other decreases, then the covariance is negative. If there is no consistent tendency for the variables to move together, then the covariance is approximately 0. The formal definition for this is given by the covariance of x, y is equal to the expectation of x minus expectation of ex into y minus expectation of ey, with these terms being in a bracket. This statement can also be expanded and written as the expectation of x times y minus the expectation of x times the expectation of y. Some useful identities associated with covariance include the covariance of ax plus by, z is equal to a times the covariance of x, z plus b times the covariance of y, z. Here, a and b are constants and x, y and z are random variables. The second important identity is the covariance of x plus y, z is equal to the covariance of x, z plus the covariance of y, z. The third identity states that the covariance of ax, by is equal to ab times the covariance of x, y. Let's talk about a useful result. The covariance of x, is the same as the variance of x. Similarly, the covariance of y, y is the same as the variance of y. These identities help us to simplify many variance and covariance calculations. Now, let's talk about correlation coefficient. Covariance tells us about the direction of the relationship between two random variables. However, covariance depends upon the units of measurement. For example, if we change the units from kilograms to grams, the covariance value changes. To overcome this issue, we use the correlation coefficient. The correlation coefficient is a standardized measure of the strength and direction of a linear relationship. Because it's standardized, it does not depend on the measurement units. The correlation coefficient is denoted by the Greek letter rho. This gives us the formula as rho of x, y equals the correlation of x, y, which is equal to the covariance of x, y upon the under root of variance of x times the under root of variance of y. Notice that the covariance is divided by the standard deviations of both variables. This standardization forces the correlation coefficient to lie within fixed limits. Now, let's talk about some of its most important properties. The most important property being that the coefficient of correlation lies between -1 and 1, both of these values being included. When rho is equal to 1, it indicates a perfect positive linear correlation. When rho is equal to -1, it indicates a perfect negative linear correlation. And when rho is equal to 0, we can say that there is no linear relationship between the variables, or that the variables are uncorrelated. Now, let's study one of the most frequently tested results in probability. This relates to finding the variance of a sum or difference of random variables. For dependent random variables, the variance of the random variable x plus y. For dependent random variables, the variance of x plus y is given by the variance of x plus the variance of y plus 2 times the covariance of x, y. The covariance term here captures the interaction between the variables. If the covariance is positive, the variance of the sum becomes larger. If the covariance is negative, the variance of the sum becomes smaller. Let's derive this formula. We start with the standard formula. As you can see, we started out with the standard formula and then expanded it until we got our final result. Next, let's talk about independent random variables. If x and y are independent, then the covariance of x, y is equal to 0. This means that the variance of x plus y is equal to the variance of x plus the variance of y. Similarly, from both of the above results for dependent and independent random variables, we can say variance of x minus y is equal to the variance of x plus the variance of y minus 2 times the covariance of x, y for the dependent case, and the variance of x minus y is equal to the variance of x plus the variance of y for the independent case. Next, let's talk about convolutions. Convolution is used whenever we want to find the probability distribution of the sum of two random variables. Suppose we have two random variables x and y. Then we define a new random variable z as z is equal to x plus y. Now our goal is to find the distribution of z. The method used to obtain the distribution of the sum is called convolution. Let's look at the discrete case first. Think of it in this manner. We want to find the probability that z takes the value z. Since z is equal to x plus y, we need all pairs of x, y such that x plus y is equal to z. Now if we choose the value x, then y is automatically fixed as z minus x. Therefore, instead of summing over both x and y, we only sum over all possible values of x, and for each x use the corresponding value of y. This gives us the PMF of z as follows. Now, if x and y are independent, then as we've covered earlier in the chapter, the joint PMF will essentially be the product of the marginal PMFs. This gives us the following formula. When a function can be expressed in the above forms, then the probability of z is called the convolution of the functions of the probability of x and the probability of y. Next, let's look at the continuous case. If x and y are dependent continuous random variables, then the PDF of z is given as follows. And if they are independent continuous random variables, then the PDF is given as follows. When a function is expressed in one of the above forms, then we obtain the convolution of z. Here we have one example of the discrete case and one example of the continuous case. The first example states that if x tends to a Poisson distribution with the parameter 2 and y tends to the Poisson distribution with the parameter 3 and they are both independent random variables, then obtain the probability of the function z, which is equal to x plus y. Now, as we can see, this statement right here follows the binomial theorem. Therefore, we apply that.
This is our final answer.
Now, as we can see, this is exactly the PDF of the Poisson distribution with lambda equal to 5. Therefore, from here, we can conclude that the random variable follows the Poisson distribution with the parameter 5. Let's look at our next example. The random variable x follows an exponential distribution with the parameter 2. And the random variable y follows the exponential distribution with the parameter 1, such that they are both independent random variables. Then we are required to obtain the PDF of z, which is equal to x plus y. Once again, we start by stating our formula. From here, we obtain our final answer. Since this does not correspond to any standard probability distribution, we leave the PDF in this form. Linear combinations of random variables. A linear combination is an expression of the form y is equal to c1x1 plus c2x2 all the way to cnxn, where c1, c2 and cn are constants. From here, we get the expectation of y as c1 times the expectation of x1 plus c2 times the expectation of 2 all the way to cn times the expectation of xn. So whenever we're finding out the expectation of linear combinations of random variables, then we simply pull out the constant and take the expectation of the random variable itself. This gives us the standard form as follows. Keep in mind that this property is always true and independence is not required. Next, we move on to the variance. If we take the same linear combination of random variables and this time we try to calculate the variance, we'll essentially start by expanding the variance into the covariance. Then, we simply input the value of y from the linear combination. This gives us our general formula. Now suppose these variables are independent. Then naturally the covariance will be 0. Then this time the variance we obtain will simply be the same as the general case, except the covariance term right here will not be there. The dependent case, however, operates on the same basis that the general formula does. Since the variables are dependent, the covariance terms remain. This gives us the following formula, which is the same as the formula covered here. Combinations of random variables. Next, we are looking at how to calculate the MGFs for the same linear combinations covered above. Before we begin with this, it's important to recall that we want to find the distribution of z is equal to x plus y. There are two main methods to do this: convolutions, which we've already covered earlier in this chapter, and the second method is MGFs. The MGF method is often quicker because we can avoid lengthy summations or integrations. The idea for this is simple and it has already been covered in the previous chapter. The idea is simple. If x and y are independent, then the MGF of x plus y is given by the product of the MGF of x and the MGF of y. In this section, we're going to be looking at how to derive the MGFs for linear combinations under discrete and continuous distributions. We start with the Bernoulli distribution. Suppose the random variable x tends to the Bernoulli distribution with the parameter p. Then its MGF is given by q plus p into e to the power t. Now suppose x1, x2 all the way up to xn are independent and identically distributed Bernoulli variables. Then the sum of all of these represented by the variable s will tend to the binomial distribution with parameters n and p. This is because a Bernoulli random variable represents one success or failure trial. Adding n independent Bernoulli variables simply counts the total number of successes. Therefore, it is natural that the result is binomial. This concept has been covered in detail in the video lecture for Chapter 2, Part 1. Now, as we know, the MGF for the linear combination of a random variable is given by taking the product of the individual MGFs for each random variable. This gives us our final MGF for s as q plus p into e to the power t n. This is the same as the MGF for the binomial distribution. Next, we move on to the binomial distribution. Suppose x is a binomial variable with the parameters n and p. Then the MGF for this is given by q plus p into e to the power t whole to the power n. Now suppose we have the same random variable x as before, and this time we also have a random variable y which has parameters m and p, such that both of these random variables are independent. Then the MGF of x plus y is given by the MGF of x times the MGF of y. Notice that both these distributions have the same success probability p. Therefore, this term for the individual MGFs is common to both. Then we add the powers, which gives us our final MGF of x plus y, which follows the binomial distribution with parameters n plus m and p. If the random variable x follows a geometric distribution with the parameter p, then the MGF is given by p into e to the power t upon 1 minus q into e to the power t, provided that q into e to the power t is less than 1. Now suppose x1, x2 all the way up to xn are independent geometric random variables. Then we define s as the sum of all of these random variables. Now, we know that a geometric random variable counts the number of trials needed for one success. Therefore, adding k independent geometric variables counts the number of trials required to obtain k successes. That is exactly the meaning of a negative binomial distribution. Thus, S follows the negative binomial distribution with parameters k and p. Hence, we have the MGF equal to the MGF for the negative binomial distribution. Fourth on the list is negative binomial distribution. Suppose a random variable x follows the negative binomial distribution with parameters k and p. Then the MGF is given by p into e to the power t upon 1 minus q into e to the power t whole to the power k. Now if we have two random variables and x is the same as given before, y follows the negative binomial distribution with parameters m and p, where p is common to both, such that both of these random variables are independent. Then the MGF of x plus y is given as follows. Again, we do the same as we did for the binomial distribution. Since this term is common, we simply add the powers. This gives us our final MGF. At last, for discrete distributions, we have the Poisson distribution. If x follows Poisson with the parameter lambda 1, then the MGF for it is given by e to the power lambda 1 into e to the power t minus 1. Now if we have the same random variable x as before and another random variable y, which has the parameter lambda 2, such that both of these random variables are independent, then the MGF is given simply by multiplying both of the individual MGFs and adding their powers. Just like we did for discrete distributions, we now apply the exact same MGF property to continuous distributions. The idea is exactly the same as before. The MGF of x plus y is equal to the products of the individual MGFs of x and y. After multiplying these MGFs, we simply compare the resulting expression with the standard MGF of the known distribution. Let's begin with exponential distribution. Suppose a random variable x follows the exponential distribution with the parameter lambda. Then the MGF is given by lambda upon lambda minus t, provided that t is less than lambda. Now, if x1, x2 all the way up to xk are independent and identically distributed exponential random variables, then we define S as the sum of all of them. This follows the gamma distribution. This is because an exponential random variable measures the waiting time until one event occurs. So if we add together all the waiting times for k independent events, we obtain the waiting time until the kth event. That waiting time follows the gamma distribution. This is why the sum of independent exponential random variables becomes gamma. This gives us the MGF of the random variable S as the MGF for the gamma distribution. Next, we have the gamma distribution. If x is a random variable which follows the gamma distribution with the parameters alpha 1 and lambda, then the MGF is given as lambda upon lambda minus t whole to the power alpha 1. Now, if x is same as before and the random variable y follows the gamma distribution with the parameters alpha 2 and lambda, such that both of these random variables are independent, then the MGF of the sum of x and y is simply the product of both the individual MGFs. This gives us the random variables x plus y follows the gamma distribution with the parameters alpha 1 plus alpha 2, lambda. The gamma distribution represents the waiting time until several events occur. So if one gamma variable represents the waiting time until alpha 1 events and another represents the waiting time until alpha 2 events, then together they represent the waiting time until alpha 1 plus alpha 2 events occur. Therefore, the shape parameters simply add together. Next, we have the chi-square distribution. If the random variable x follows the chi-square distribution with the degrees of freedom alpha 1, then the MGF for this is given by 1 minus 2t to the power minus alpha 1 upon 2. Now, if x is the same as before and y follows the chi-square distribution with the degrees of freedom alpha 2, such that both of these random variables are independent, then the MGF of x plus y is given as the product of both the individual MGFs. This gives us x plus y follows chi-square with the degrees of freedom alpha 1 plus alpha 2. At last, we have normal distribution. If x is a random variable which follows the normal distribution with the parameters mu1 and sigma square 1, then the MGF is already known. Now, if we have another random variable y with the parameters mu2 and sigma square 2, then the MGF is the product of both of these. Therefore, x plus y follows the normal distribution with the parameters mu1 plus mu2, comma, sigma square 1 plus sigma square 2. That brings us to the end of this week's video on Chapter 4. I'll be back next week on Actuarial Simplified, where we'll be discussing conditional expectation. See you next week.